Okay, so yeah, neural networks start off with this is like now that you've actually processed your data, like how are you actually going to be able to use that data to make a model? Um, oh yeah, and just as an intro again, I'm going to have the slides every time, but this is the workshop. We have the competition under the theme written in the stars. So if you found a data set for that, then you can make an AI for it. It could be any kind of AI, but we're specifically doing a neural network in PyTorch, which is kind of like what a lot of almost all AIs are made with nowadays. Oh, that's meant to say this meeting, but yeah, this was last week's slides. This meeting's in 2:15. Next week it will be in the normal location on like the fifth floor or whatever. That's just this week because the room was booked. The submission is due already in like 3 weeks. So just oh wait, I think it's 4 weeks, but we're only gonna have like 3 workshops. So keep that in mind. Because I think we don't have one Thanksgiving break, like the week where Thanksgiving break is happening. Yeah, so how are we actually going to make the neural network? So in the previous times, we talked about like, okay, you have a bunch of data, like, I don't know, weather data or something, or data about pictures of dogs and cats, and it's trying to predict if it's a dog or a cat, right? And basically I just said, okay, you have the, I don't know, here's a picture. Actually, let's say it's a picture of a person, right? And I kind of just had the model as this black box, right? And then it outputs, the person, let's say. Like let's say there are three options: person, dog, or cat, and then output that it's a person. So that was correct, right? Um, but I didn't actually specify, okay, how does this model actually work, right? I said that, okay, basically we have a lot of images, like thousands and thousands of images, or at least hundreds of images and each one says, this is a person, this is a dog, this is a cat. We feed it through the model, it makes a prediction, and we tell it whether it's right or wrong. And based on that, it can improve because it knows whether it was right or wrong. And we're going to go a little bit more in depth with that because once you have the data set, then this model can learn from it very effectively. So it's kind of just an overview. So let's start with the most simple model, which, I mean, it might not look that simple from the image, but trust me, it's all multiplication and addition. That's it. So on this perceptron, I'm actually going to draw it on the whiteboard to make it more clear. You have this. I'm just going to represent it as a circle. You can just imagine it's basically a number. And you have your inputs. So let's go with the example of like, it'd be easier for something with like less inputs. So let's pretend, I think last time I did an example of temperature. So let's say your inputs are, I'm predicting the weather basically. So the inputs are like humidity, I don't know, air pressure. What are some other ones you guys can think of? Um, Maybe like yesterday's temperature. Right, and these are all numbers, so it could be like 72. The pressure was 4. I don't really know what that means. The pressure here was 7. So these are just numbers, right? And we're feeding them into this perceptron. What does it do? It multiplies each of these numbers. So let's say 7. It multiplies it by what's called a weight, and that can be any number for now. So I'll just say in this case, let's imagine this line here. We kind of represent it as a weight. On the image on the slides, there's a box, but I'm just going to draw a line. Let's say this weight is 2, right? So 7 times 2, that's 14, right? And it does this for every line. So let's say the weight here was -1. Then the output here would be -4. And what it does when there's two inputs combined, it just adds them together. So 7 times 2 is 14. 4 times -1 is -4. So -4 plus 14, this becomes just 10. And then, I don't know, so 72, let's say it's times 0.1. So that's 7.2. So it becomes 17.2. Does that make sense how that works? Yeah. It just multiplies each input by a number, and then that becomes the output. And when we send this output, sometimes you'll see it actually has multiple outputs like this. Really what that means is it's just copying this number to both outputs. If you ever see a perceptron with multiple outputs, each output is the same. It really only has one output. So I'm just going to draw that as one output for now. And what's important here is that these weights, right? So these weights can be any number, and often they're drawn with the letter W. You'll see there on that image, right? And you can ignore the activation function for now. Just imagine that does nothing. W1, W2, W3, right? And obviously the output of this perceptron is determined entirely by the weights, right? If you have different weights, it's going to output something different. So our goal is kind of figure out, hey, how can we get these weights to the right values? And I'll talk about that more. Does that kind of make sense? Yeah. So the thing is now we've got to consider, okay, that's cool. But this obviously is like ChatGPT doesn't just multiply each word in and then output something, right? It's obviously got to be more complicated than that, right? So how can we make this more complicated? Well, what if we had what are called multiple layers? So I'm just gonna kind of make this smaller, but it's still the same exact thing, right? So we have, and let's not specify these numbers, they could be anything. What if we had a perceptron here and a perceptron here, right? So this one would take all these inputs, right? And this one would take the same exact inputs, right? So that's kind of what it looks like. And then each one would have one output, right? That kind of makes sense. So these weights for each perceptron would be different. So even though they're attached to the same inputs, they have different outputs because each weight here is different. So this could be 5, but this one could be 4. So this one could take the community and multiply by 4, whereas this one would take the community and multiply by 5 or -2 or any number, right? So the outputs here would be different, but we're just predicting one thing, which is the temperature. So we can have another perceptron here, and this one would be connected to each one here, and then do that. And what happens is now this perceptron is taking out the output of this one and also multiplying it, and also multiplying the output of this one, also adding it to this. And once you do that, you can just start stacking more and more of these, right? Right? You can put more here, you can put more here, right? I'm not even going to draw all these lines, but like, and you can keep adding more and more layers. Does that kind of make sense? How you can add more layers like that? And all these are doing is multiplying and adding. Each of these lines, basically, you can think of it like multiplication, and then inside the circle, they're being added together. So this is what we call a neural network, because you can see there's obviously like a network of lines here. And neural kind of, it's emulating how neurons are kind of connected one to the next, to the next, to the next. Specifically, I'm going to go over some of the like terminology here for this, because it's going to be kind of important when we're talking about later, especially if you're going to be programming this, they'll probably not going to be using words that I'm using. These here are called the inputs. You probably already knew that, but they're also called features. So inputs are features. This is obviously our output, right? But one thing we have to consider about our output is it can take lots of different forms, right? Like in the case of temperature, I'm just predicting a number, right? So 72.4, right? Or I'm predicting 80, right? It's just a number that I'm predicting. This is what's called a regression. So in this case, I'm only predicting one number, so my output is one neuron. A regression just means I'm predicting a number in a range. Theoretically, you can do like multiple regression, which is like where you have 2 outputs, and that's totally fine. All you do is you just have 2 perceptrons on the output, right? The other thing you might be thinking of is what about the example with the dog cat, right? Or the dog cat person, right? Like in that case, it doesn't make sense to output 80, right? Like what does that mean, dog or cat, right? In that case, what you actually do is you have, let's say I have 3 classes, dog, cat, or person. And let's just make this more symmetrical. I would actually have 3 output neurons, and each one would be correlated with dog, cat, or person. In the example I was showing with the images, obviously your inputs would be different. And the output here is just what's the confidence of the neural network that it's a person or a dog or a cat. So it might output like 0.7 for person, 0.2 for cat, and 0.3 for dog. And these don't even have to add up to 100%. Sometimes it can be confident in 2 of them. But they're usually between 0 and 1. So in this case, you would say, okay, the neural network thinks it's a person because person is way higher. Does that make sense how you do kind of what's called classification, where you're choosing a class, or regression, where you're just choosing a number? Okay. So we can have our inputs or our features, and we can have our outputs or or outputs, which can be in different forms. The ones in between here are called hidden layers, kind of because we don't decide them directly. That's just what they're called. Important. And then the last thing I want to mention is what these things are actually called also, these circles. I call them perceptrons, but really often they're called neurons or just nodes, like just one of these circles. And they're called neurons, so that means this whole thing is kind of called a neural network because each of these is like a neuron, quote unquote. One of these is called a layer, just like one vertical stack is called a layer. And specifically, actually, you can have different kinds of layers, but the most common one is this kind, which I'm teaching you about today, which is a linear layer, or a perceptron layer, I guess you'd call it, or you'll sometimes hear it called a feed-forward. So linear, why is it called linear layer? Because it's just multiplication and addition. And multiplication and addition are linear operations, right? And maybe I'll give you a hint for something later. But think about what linear means here for these layers. And then this whole thing altogether is called a multi, we'll put that at the top, multi-layer perceptron.
Whoa.
I know, right?
You guys have any questions?
No.
Are you sure?
Yeah.
Okay.
Yeah, so, I mean, obviously, because it's multiple layers of perceptions, right? It's also just called a neural network. Technically, neural network is a more broad term because you can make all these neurons kind of, like you can connect them in different ways, basically. But a lot of times people say neural network, this one, which is multi-layer perceptron. Or both. Yeah. Sorry?
I have a question.
Yeah.
So each one of those layers, you said that it's in charge of multiplication, like the linear multiplication you said.
Yeah.
So is that happening in every one of the layers or just like the first one?
All of them. Yeah. So let's say I have a humidity here of like 5 as my input. And let's take, for example, this neuron has a weight of 1 for that humidity. This one has a weight of 2 for that humidity. Then 5 would get multiplied by 1 and would get put here. And 5 would get multiplied by 2 would get put here. You get 10. So it makes sense. There's 10 here and there's 5 here. Then it would add together all the other inputs, which I'm not going to do because that'll take a long time. But let's say it turned into 17 after it adds together like the pressure and the yesterday's temperature and whatever other inputs we have. And let's say this one just stays at 10. Then the same exact thing would happen. This output would get multiplied as it goes to here. So let's say this weight here for this specific one is 2. It'll get multiplied by 2. You get 20. And then this one would also add together all the ones. So in addition, it might have a weight for this one, for this 17. And this 17 would get multiplied by whatever weight. Let's say it gets multiplied by -1. So then it would be actually -17, which means this 20 would become 3. So as it goes through, each weight number gets multiplied, it gets added, it gets multiplied, it gets added. There's actually a shit ton of multiplications and additions going on and on and on.
Yeah. So to put it simply, each node does an operation, usually a really simple one on the data.
It's always multiplication.
Oh, yeah. Oopsie. Yeah, it always does multiplication, which wouldn't seem like it's very useful, but in aggregate, it comes together to usually produce a useful output if it's well trained.
Yeah, so you can think of it here again. This node that's taking each input and multiplying it, that's the same exact thing here, except for the inputs happen to be inputs that have already been multiplied and added here. And that's actually part of the reason it is simple is so that it can be run thousands and thousands of times super quickly, right? If it was some super complicated operation, GPUs wouldn't be able to run it like fast enough because it has to be run literally in like, nanoseconds.
So that's the thing about ML that I feel like isn't emphasized enough, because ML is really, it takes a lot of time to train models, right? But once you put them in practice, they're usually really, really fast and they're really efficient. That's why it's useful.
Yeah, the training process, because you have to compare it to thousands of examples, takes a really long time. But what's called the forward process, where you take an input and get an output, is usually much faster because it just has to multiply them. That being said, there is one extra thing, which I've been saying this is all linear and multiplying, right? But there is one thing that kind of prevents us from making it just multiplication and addition. And that's basically a property of anything that's linear, which is that you can distribute, right? So like, let's say I have two numbers, I don't know, 4 plus 3, and then I multiply them by 6, right? Like, and then let's say I don't know, I add 3. You kind of think of this as a perceptron, right? It's like taking its inputs, multiplying them, adding them. The thing is, you can just distribute the 6 in, right? And it becomes just, 6 times 4 plus 6 times 3 plus 3. And instead of this being like 3 different operations, it becomes just 1, which is, you can just multiply. I mean, you can imagine this is one number. It just becomes 1 operation, right? And what happens here is like, let's say I take this input 5 and I multiply it by 1 here, and then I multiply it by 2 here, right? Then I get 10 here, right? But the way multiplication works, taking 5, multiplying it by 1, or let's make this more complicated, I guess. Taking 5, multiplying by 3, then multiplying by 2, you can just do that as one multiplication, right? The issue is, and same thing with addition. When you add numbers twice, it's just the same as, you could rewrite that as just being one addition, right? When you multiply a number twice, you just rewrite that as being one multiplication. So what happens is that if this is purely linear, it all basically just becomes compressed because this can be one layer. And you get all this complexity that I've kind of built up with these multiple layers is kind of gone. Because each multiplication could just be kind of, it isn't any different from one layer.
And that is not useful to us.
Yeah. And the reason we don't want it to just be one layer is because when you have just a couple inputs, right? And you have this, all it's doing is multiplying and adding inputs. And if you know, we don't want our outputs to be linear. Because if you know anything about linearity, what that means is basically that's a straight line. Right? Like let's say this is y equals mx plus b, right? And the fact is, most of the time our data, like whatever you're doing, like choosing a cat or a dog, that's not like that's not a straight line division of data. Our data is way more complicated than that in the real world. So we want to make our model not linear, and we want to preserve this complexity that we built up, right? We don't want it to just kind of collapse into a linear layer. So how do we do that? What if we, instead of having, this distribute back into here, what if we somehow put like, just a different color. What if we somehow put like blocks in between here that prevent the linearity from kind of distributing? It's called an activation function.
Whoa.
Yeah, which sounds complicated, but it's really not that complicated.
Yeah.
It's just something non-linear that we put in between that prevents it from distributing, right? If you consider with my example of distributing, you can't distribute into a non-linear function because it's that's kind of like what the definition of nonlinear is. And so basically, we just put something in between here that just is not linear. And it could be literally anything. So anything that isn't a straight line. So I don't know if you guys can think of any non-linear functions.
X cubed.
Yeah, x cubed is non-linear, right? It kind of looks like this, right? That's not this does not draw. X cubed looks like this, right? So that's not a straight line. Any other ones?
Squared.
Squared, yeah. Also not a straight line. So we usually choose a function that's nonlinear called ReLU, which is also kind of super simple. Like we just take this line, this straight line, right? And we just bend it like that.
Yeah.
And what it does is it's super simple. If the output is less than 0, it becomes 0. If the input is less than 0, it becomes 0. Otherwise, it stays the same. So I'm going to draw this ReLU as kind of just a block. And again, it's just a function. So let's say I put in the number 5. What's going to be the output? 5. If I put in the input -4,
0.
the output is 0. So this is kind of going through it, right? The input 6, it just stays 6. But anything that's negative will just become 0. So it's a super simple function. Again, part of that simplicity means that we can run it super quickly and train it super quickly. And it prevents us from distributing because it's nonlinear. We can't necessarily distribute over it. It no longer becomes like distributable.
But Anthony, why don't we use x cubed or x squared or x to the fourth?
Yeah, so generally x squared actually is still x squared basically these ones, you'll notice that they get very big very quickly. Like exponentials, right? Like 5 cubed is already like 125. It's super huge. And that kind of makes the neural network super sensitive, and it has to like use very like small differences in numbers, right? Because a very small difference is ultimately very big, like exponential. And just with how modern computers work, especially like we can't store super tiny precision numbers. So it's easier to just use a simple function like this.
Computers do not like big numbers.
Yeah, because like the way computers store numbers, like if you store like 5.00001, like this is actually a lot of storage just to like say that it's the 5.0 number. And it starts to have really bad math because it gets less precise. The other function we sometimes use is sigmoid, which is kind of more complicated, but it basically just is a smooth slope between 0 and 1. This was actually the original activation function, I believe, or maybe it was a step function, but it was one of the earliest ones used, like even in the 60s or something. And it's literally just like this, it's 0, 0, then it kind of goes up, and it's, let's say this 1. And then it kind of goes to 1. I mean, actually, it doesn't like hit 1, it like approaches 1. And same thing here, it like approaches 0. But that's super simple where it also just keeps the input between 0 and 1, and then it kind of smoothly transitions between them. The reason you might want this one, I mean, sometimes people still use it, but also sometimes you put it on the output to make sure that the output is between 0 and 1, because no matter what number you put in here, the output is always between 0 and 1.
Wait, so it never approaches 0 or 1 with sigmoid, or?
With sigmoid, I mean, the thing is computers aren't perfectly precise, so if you put in like a super high number, will output 1. Mathematically, the calculation is like asymptotic, so like it gets closer and closer and closer to 0. It's like 1 over e to the thing, so it uses e to the negative x, which, you know, like e to the negative x also like approaches the number. But really, most of the time you're going to be using what's shown on the slides, which is this ReLU. Super simple, just negative numbers become 0.
Yeah.
So now to show you again with a concrete example, we have this perceptron. Its output at the end, I'm just going to put this little blue blocks. ReLU. Right? Before it sends it to the next place. If we output 5, 1, and 7, then the output depends on the weights still, right? In this case, I'm just going to pretend the weights are like, 1, 2, -3. So 1, 2, -3. So 5 times 1 is 5, plus 1 times 2 is 7, minus 21. Actually, whatever, that's a negative number point is, right? So the output of this is a negative number.
So it's going to be 0.
So the output is always going to be 0. Yeah. Now, if I input something different, let's say this input was actually 1 and this one was 10, right? Now it's 20 minus 3 is 17. 17 plus 5 is 22 is now the output here. So this is actually going to output 22. So if we go back to our neural network slide, you can see that's exactly what this is doing, where it takes each input, weights it, and then it has that activation function, which is just anything that's nonlinear. In most cases, it's ReLU. Sometimes you'll see some other ones. And which activation function to choose is still kind of an area of research. So like there's recent like improvements been. Some people have like kind of modified ReLU to make it like smooth. So instead of being, like this, and then there's this little edge here that's kind of discontinuous. So some people have made like a kind of newer activation function, which tries to like kind of smoothly move up to 1 like that. And that one's called, I think, like ELU. So there's still like active areas of research where like different ones are being used, but ReLU tends to be the standard, and I really doubt you'll have issues using it.
Is ReLU an abbreviation for something?
Rectified linear unit.
Rectified linear unit. Yeah, which is like such a overcomplicated name.
Don't worry about it. Just
Rectified.
the bendy thing.
Yeah.
Just remember that. Easy.
Okay, so basically what we've been doing so far is like, we have a bunch of inputs. and we multiply it by a bunch of weights, we do the activation, right? But really, the output is going to be completely random, right? Like if we set the weights randomly, then the output will be random, right? Or it won't be random, it'll be predictable, but like the output will be wrong, right? So how do we actually choose the weights so that it gives us a correct answer, right? That's the most important problem, because now the output of this neural network, it's complicated. It's super complicated because it has all these layers and does a bunch of math, but all that math depends entirely based on the weights. So now what we're trying to do is using the training loop, we can use the data to adjust the weights to get actually correct values. So for there's some set of weights such that all of these multiplications make out the right answer. So basically, I'm going to go over this at a high level, and I'm going to go in deeper. So at a high level, you have your training loop, right? And this loop basically will run, over all of your data a couple, I don't know, 100 times or something. And the first thing is you get a prediction from your inputs. So you call your model. It's kind of like pseudocode. So you put your inputs into the model. So let's say you have a bunch of, I don't know, in this case, I guess I was doing weather. So you have a bunch of data about the weather for like a couple of years, right? So you feed in, here was the humidity, here was the pressure, here was the temperature, and you get an output, right? And it will just multiply it, it'll do the relos, it'll do all that stuff, and it'll give you an output. You tell it, okay, what was the temperature on that day? And it tells you the temperature was, let's say you look at the last, there's only one neuron on the output because there's only one output here. Let's say it says the temperature was, the output's the number 5. You're like, okay, that's wrong. The temperature on that day was actually 72 degrees, right? So this 5 is your prediction. And now you need to see how wrong it was. So that's very simple. It's something called loss. You can basically just see how far away is it from where it's supposed to be, right? So in this case, I guess it was 68 off, 67 off.
I think a good way of thinking of loss is just how shit your model is at the time.
Yeah. So you want your loss to be as low as possible, right? You obviously want this to be 5, and then your loss, or you want this to be 72, and then your loss would be 0, right? So you would do this because you don't want to just train it on one example. You do this over a bunch of examples, right? So you do it another time, and it outputs 800, and the right answer was 80 degrees, right? You do it another time, it outputs 60, and the output was, I don't know, 72. Sure, let's say it was 60 actually. Right, so in this case, the loss was 68. In this case, it was 720. In this case, it was 0, right? Or that actually depends on our loss function. So you would want to actually average the loss, right? Actually, wait, I was going to say, okay, but basically based on this loss, you are able to update and score and update these weights to slightly make your loss lower. That's the high level overview. Sorry, I was getting into the lower details. Okay, so how do you actually get the loss here? So the most common thing is what's called mean squared error, which is very simple. The mean means the average. So you have a bunch of examples. In this case, I only did 3, but really it'd be whatever, 100. You take the average. So how do you calculate average? 1 divided by the number of times. So basically 1/3, but I'm just going to say n because whatever the number of examples. And then you add together your errors. So let's say in the case it was 72 minus 5 plus, I don't know, whatever, 800 minus 80, right? Et cetera, plus dot, dot, dot. Similarly for repeated addition, I'm going to use this symbol, sigma, which just means you're adding it up a bunch. So this just means taking the average, and we're actually going to square the difference. So let's say we have, I guess, predicted square. So why might we square the difference? Well, one reason is kind of obvious, which is that let's say output is 5 and the actual is 72. Then that means the predicted was 5. minus the actual was 72, you're going to get a negative number here, right? So you're like negative 68, right? Negative 60. And if it's trying to lower the loss, a negative number is a bad thing, right? Negative numbers are technically lower, so the machine is just going to always predict really high numbers and get lower loss. So you don't want a negative number. And the nice thing about squaring stuff is it always outputs a positive number. You might think, okay, why don't I take the absolute value, right? Because that will literally just give us positive value. Thing is exactly the same reason we're talking about now. Actually, big numbers are kind of good for us in that if a number is very close or close enough, we don't really care about it. But if a number is super far away, we want to really focus on that example and why it's super far away. And the good thing about square, I mean, if you just look at the graph, right, is it just becomes really high really fast. And so if you're like really far away, your loss will be super high for that example. And it'll kind of focus on those examples where it's really wrong. But there is actually something called mean absolute error, MAE, instead of mean squared error. And you can use that. It is something in PyTorch that's implemented. And you can use it if you'd like. It's sometimes a good thing if you have like, I don't know, a lot of outliers that you don't really want to care about or something, then you can actually use mean absolute error. The other nice thing is that squared is actually like a continuous function, which means it doesn't have like a little corner at the bottom. But that's just kind of for the math side. That's not really as important. So again, we calculated the loss. So this is basically how bad is the model. We take a bunch of predictions, which I've talked about previously, just multiplications and the ReLU stuff in between. We take a bunch of predictions. We see what the actual result is. What is the actual result supposed to be? We take the difference, we square it, and then we take the average. And that basically tells us, okay, how shit is your model? If it's really bad, that means, okay, I need to change my weights a lot. If it's not that bad, the loss is very low, it's close to zero. Maybe I only have to make some minor adjustments to my weights. Because again, the output is determined entirely by the weights. By adjusting the weights, I can get any output I want. Does that make sense so far?
Yeah.
The one thing you might wonder is, okay, but what if my output was the example where I was classifying, I don't know, dog. Okay, let's do like a different one. I don't know, like, what was it? There's any examples of AIs that classify stuff?
Book genre.
Book genre. Yeah, okay, so sure. So let's say you have, I don't know, 3 outputs. If it's like, I don't know, nonfiction, I'm just gonna write NF. If it's romance, or if it's sci-fi, I don't know. Right? And let's say it makes a prediction that this was a romance novel based on some inputs about like who wrote it, maybe what's the like, I don't know, what's the like plot summary, whatever. It outputs as romance. And the actual answer was nonfiction. How are you supposed to subtract these and square the results, right? It's not really possible, right? So that's why specifically for classification, you have to use a different kind of loss function. Specifically, again, remember these, we can translate, let's say nonfiction. We can translate these a bit into numbers, which can help us, which is that it will output, again, some probability. So let's say it actually outputted 0.8 for nonfiction, and 0.1, and then 0.2 for sci-fi. And basically what we say when we say that we want the result to be nonfiction, we just say 1, 0, 0, right? So we say we want this to be 1 and we want these two to be 0. But they're still kind of taking the difference here, and like, it's still, because our output isn't really like a range, it kind of doesn't really make sense to take the difference and square it here. So instead what we do is we do what's called cross entropy loss, which is, the calculation is a lot more complicated. So I'm not going to go over it, but you can look into it. But it's basically saying, it kind of makes it so that these like inputs that are kind of close to 0 are less important. And it kind of says like, what's the like, entropy is like a measure of information of something. So it's saying, okay, how much information am I actually getting from like what this output is telling me? So this is telling me that it's nonfiction. So it's like actually a pretty good output. But you can look more into that because honestly, we have like a whole lecture on that, I think, basically. The actual Sky lecture instruction meetings. But yeah, in PyTorch it's implemented for you, so you really don't have to worry about it. The other thing you might use is binary cross entropy. So let's say you have actually only two examples. So this is a binary classification problem. Binary means two. In this case, you actually don't need two output neuron nodes. You only need one. And they see zero. Let's say if we have an example of, our example is classifying if an email is spam or not spam. Right? This is a very common use of AI. So we would just say spam means one and not spam is zero. One is zero. And our output, then we would only need one neuron and it would just be a number like zero. If it's not spam, 0.5, maybe if it's not sure, et cetera, et cetera. And just for that, we would use slightly different algorithm called binary cross entropy, which is slightly more optimized for this. But same thing, basically. Okay. So now we can have a measure of, based on our weights, how bad is the neural network, right? Now we need to take that loss, right? That's what loss is. And we want to try to actually update these weights inside. Ooh, okay. I meant to talk about this. Okay, when we do update the weights, we do actually have to do something which is called splitting between train and test. I'm not sure if I introduced this to you guys previously. No, maybe not.
I don't think so.
Okay. So very important is splitting the data into training and testing data. And you can think of it very similar to like an exam your professor would give you, right? Usually your professor doesn't give you the questions and answers to an exam to test you, right? Because he wants to know how you actually perform, you know, if you're just given those questions without knowing the answers, right? So in the same way, when we have our data set, let's say a bunch of pictures or whatever data set of the temperatures or of the spam or not spam or of the books, we actually split the data set, usually about like, I don't know, like 70% and 30%, where the 30% is called testing data, and this we would call training data. And this is 7, sorry. It's like 70 or 80% training usually. This training data, we feed it through the model, we have an output that it predicts, and then we use that prediction to get a loss, and then using that loss, we update the weights, right? The issue is that if it's training from these examples, what it can do is it can basically just learn all of these examples if the neural network is smart enough. What we want to do is we want to evaluate how well it's doing on stuff it hasn't seen before, right? What happens is what's called overfitting. And this is kind of what's shown in the picture, but basically it's memorizing where each of these examples is.
Oh, actually, I think you did talk about this. Like, if it takes like a picture of like a dog, it memorizes the like pixels of like the picture, then shows like a similar picture of another dog, but it's different. And then like it doesn't classify that as a dog because each pixel isn't exactly the same as like.
Yeah, exactly. And if you look, that's exactly what it's doing. Is instead of we want this neural network to learn general rules, right? We want it to be able to use examples in the real world that it hasn't seen before. Like if you're training, like I think a car and it's like trying to recognize like stop signs or something. If it only learns the stop signs that are in your data set, you want it to make sure that like, okay, in the real life when it's driving, it sees the stop sign outside and it stops. Otherwise that could be catastrophic, right? So you leave some testing data that the weights aren't updated from. That way it can't actually learn these specific examples and like put it into the weights and learn from them. The example here on the slide is also kind of a simpler example where you just have one input and one output. And you can see here on the left, it's like a good model, right? It's learned a general rule that basically, okay, the points increase as the input increases, right? That's the black line. The blue line is the data set. Meanwhile, here, the blue dots are the data set and the black line is the model. Here, it's basically, it hasn't actually learned the general rule. It's just literally going to every single point and then not actually finding out what the general rule is. So like if I had a point, for example, right here, okay, this mouse is not moving. Okay, but if I had a point like right in between those points, it would actually do worse on that line. Or if I had points that were further out, it wouldn't really know how to classify them. It's not generalizable to like real world stuff. So to represent that, we always split part of our testing data later. Okay, so now how do we actually update our weights? And remember, we only do this with the training data. So it's called an optimizer. And so I talked previously, the output of the model depends entirely based on the weights, right? So I'm going to then draw a graph. Let's see. We can literally do this. The weights. Or I'm just going to do an example of one weight. So let's say, I don't know, in this neural network, this neuron multiplies this one by a weight. And let's just graph what that weight is. So let's say that weight could be 4 here, and it could be, you know, whatever number here, right? This is what the number of the weight is. Actually, let's probably put 0 here, and then it can be negative. So let's say -1, no, -2, -3, 1, 2, 3, right? And this is literally what is multiplying by, right, in one of these neurons. It doesn't matter. We'll just choose one of these examples. And we can say that when the weight, let's say we pass through a bunch of examples, and we have the weight, we started off randomly. So let's just choose a number. Let's say it starts at the weight is 1. So it basically just multiplies the input by 1. And we calculate a bunch of examples. And like I said, we calculate the loss. And we can see, okay, with the weight of 1, our loss was pretty high. I don't know, whatever number this is. Again, it's mean squared error. So the loss was pretty high, right? We can literally run our model over all those examples, calculate the average loss, and get a point here. And what we can do at that point is we basically have a bunch of examples. So that point kind of looks like maybe even scattered over a bit. And with math, that I'm not going to really get into, we can imagine that, well, here, let's restart. We have the loss that we calculate from this weight, right? If we imagine this, we can do that for every weight, right? And we can imagine that our function looks something like, I don't know, like let's say like it looks like this, right? So like theoretically, if you have a weight of 3, your loss would be this high. If you have a weight of 2, your loss would be this high. And so what weight would you want in this example?
-3.
Yeah, like -3, about,
Yeah.
like whatever it is here, right? You want your loss to be as low as possible. So what you basically want your optimizer to do is to choose, or what your optimizer does do, is it tries to choose the weight that is at the lowest point, right? Now in this case, it's pretty obvious, and you can look at it and see, right? But what's really happening most times is you don't know this graph, right? And it's also constantly changing because your examples are changing, right? So really what you have is a tiny little point here and a tiny little section. Let's say I have out 1. I have a tiny little section of this here, right? That's actually visible to me. So how does it find the lowest point? What it does is for that section, it sees what the slope is. So if you imagine like y equals mx plus b, this is just what is the actual like line there. And it basically just says, okay, I can see that the slope is going downwards that way. So I'm just going to go downwards this way. And it makes a tiny little step in this direction. So in this case, it would make a step this way, and it would say, okay, clearly the slope is going downwards to the left. So instead of being 1, I'll do like 1.5 or something, right? It would be even smaller for a real life neural network, but I'm just going to get a little bit faster. It would step this way. And it would see, oh wait, the slope is here is also negative, right? And it would go here. See, the slope is also negative. And it would keep going like that and like that. And you can see eventually this would try to get to the lowest point. And if it was here, the slope would be like this. So it would know to travel kind of down the slope. This was called gradient descent. Gradient, because this process of finding the slope, which uses a derivative, is called a gradient because usually it's in multiple dimensions. And then descent because it's going down a hill, basically. It's descending. If you look at this example on the slide right here, you'll notice that's exactly what it's doing. Except for now, instead of having only one weight, which I've drawn on the whiteboard, it has 2 weights. In this case, one of the weights is the x-axis. The other weight is this, I guess, y-axis. And then the loss is the z-axis, right? I notice each ball represents kind of a different optimizer. And all of them eventually try to get to the lowest loss, which is over here in blue.
Any questions?
So there's a couple parameters here. One thing is that they do actually factor in more than the slope. Specifically, one of them is, hello. Wait, what's that?
One.
Ooh, okay. Specifically, one of them called atom optimizer. It also tries to give the ball that's kind of rolling down a little bit of momentum. Why does it do that? Well, it's kind of illustrated here is, let's say it goes here, then it makes another step, it sees it's negative. It could step here, right? And then the slope will tell it just go back down, right? So you can't rely purely on the slope. You kind of, what Atom does is it also relies on kind of some of the previous slopes to kind of try to get over small hills like this. And it will kind of, even though the slope here is pointing that way, it will actually kind of go over this hill and ignore that for a little bit. Try to help it get to here. The other thing that's very important with optimizers, and this is something you're going to have to choose, is what's called the learning rate. I'm going to call it LR. This is basically deciding how big of a step you want to make, right? So when I said this step here, right? Let's actually redraw this graph. And I'll draw it the opposite way. Right, let's draw this. All right, it's not that. If you make too big a step, then first off, I mean, this is basically representing you're learning how to move your weight based on the input. If you make too big a step, you're basically making a huge change to your weights from just a couple examples, which is a bad idea. Like one representation in here is that, like, let's say your slope here was like this. You would say, okay, move to the left. You move way too much to the left, you could jump over here. And you totally miss this huge, like, improvement, right? So you want to make very small steps usually. So the learning rate is usually like 0.001 or something. So not that, like a very, very small step that you're making. The other example is maybe if your learning rate is too small, it will, let's say the slope here, let's say it's on kind of a much more flat slope. Or actually, this is a pretty good example right here. Let's say it was here. And your learning rate was super small, and this slope, it actually calculates based on the left slope. So if it's on a steeper slope, it'll go faster. If it's on a kind of flatter slope, it'll go slower. It will be a super small slope, and then your learning rate, let's say, was way too small as well. Then it would make such a tiny step that there would be no difference, and it would take super long to train. So you want to make your learning rate kind of pretty small, like 0.01 range, but you don't want to make it so small that it doesn't move, but also not too big that it doesn't like kind of learn from too few examples. And generally, you just play around with it and see what happens when you change it. If you find that your model isn't like changing at all and it's always outputting kind of similar stuff, maybe you need to increase the learning rate. If you find that your model is kind of like too erratic and kind of always performing differently or like isn't like converging, then you might have to decrease your learning rate. But that's something you can play around with and just see what happens. Good. So lastly, the overview. We talked about a lot of stuff. So this is basically going to be the format of your code. So first, you initialize your neural network, right? This is the amount of layers you have. This is also the width of the layers. You're going to initialize your data into training and testing data. You're going to initialize your optimizer. Usually you're going to use the atom optimizer because that's basically the best one. And it will make sure you get over those hills when I talk about it. You're going to choose the learning rate for the optimizer. You're going to initialize your loss function. And the loss function, like I talked to, is probably mean squared error. Or if you're doing classification, it might be cross entropy loss. And when I say initialize, it's super simple. PyTorch gives you basically all this stuff. So for the optimizer, PyTorch gives you the atom optimizer. For these layers, PyTorch gives you what's called NN. I'm going to just say it right now, NN.linear. NN.linear layers. ReLU activation, it gives you that as well. It gives you sigmoid, it gives you like a shit ton of activations that you can use, but I would use ReLU. And so all this stuff is literally just saying like layer 1 equals NN.linear. Right? And NN.linear is imported from PyTorch. You know, loss equals M mean squared error, MSE, and MSE is imported from PyTorch. So that's pretty simple. The initialization is mostly just making sure and deciding how like wide do you want each of these layers to be and how deep, like how many layers you want there to be. Then you want to make the training loop. And this is basically like literally a for loop where you put in the inputs into your model, which is made with PyTorch. You put the inputs in, it will spit out an output. So this would literally be putting stuff into these layers. So you do like, you know, let's say I define layer 1 here. I do layer 1. And then I do input. And then I say out. Out equals layer 1 input, right? So PyTorch makes that super convenient. That will give you a prediction. Then you just use that prediction with whatever your thing is. So you just pass in here's what it predicted. Here's what the actual output was supposed to be. And it will give you a loss. Then with that loss, you can update the neural network using the optimizer. And that's super simple. That's like optimizer.step. And it'll do it automatically for you too. Then the last thing is you want to evaluate how your model is performing on real world data, or not real world, but basically data it hasn't seen before, right? So you do the test loop. And that's the exact same, except for, again, you cannot update your weights on the testing data, right? Because if you update your weights on testing data, it could start to try to memorize them and then kind of it'd be as if your professor gave you the test answers and questions before the exam, right? It wouldn't really make sense to test on stuff that it could learn from. So you just make a prediction and you just calculate the loss. And basically what you would do is you would see, is my loss on the testing the same or similar to my loss on the training? If your loss on the testing is super high, but it's super low on training, what that means is that it's super low on training because it's memorized your training. And it's super high on testing because it's basically just memorize your training, but that doesn't work on real world stuff. So in that case, you need to adjust your model somehow to account for the fact that it's been overfitting. And I mean, it's kind of intuitive how it could memorize the data. It memorizes the data usually if there's too little data. There's so little data, you can just memorize each one. The other, sometimes what happens is the reason it can memorize the data is that your neural network is like really huge. And your neural network is so huge, it has so many weights that it can just memorize the data in those weights. So you might need to make your neural network smaller. So that's kind of like, this slide is really kind of an architecture of what your code is going to be, which I'm actually going to talk about at the next meeting. Okay. Oh, wait. Okay, this looks super complicated. And I don't know, are you guys thinking of doing images?
No.
Sai, are you thinking of doing images?
No, I don't think so.
Oh, okay. In that case, I'm going to go over this super quickly so you're kind of aware of it. But also, maybe some people who are watching this recording maybe will be interested. One thing with images is there's kind of two problems. One thing is that these neurons, these inputs, for an image, each of these inputs would be a pixel, right? The issue with that is that like the order of these inputs doesn't really matter, right?
Wait, so like it would be like RGB?
Yeah, RGB. So let's say, yeah, it would literally take like, let's say you have an image and it would take literally like, the first pixel here, it has 3 values for RGB. Let's say it's 1, 4, 3. Actually, I guess it's between 255. So it'd be like 255. So it's basically RG. It's just basically a blue pixel, right? It would literally feed in 1 here, 4 here, 255 here.
Okay.
Yeah. The issue is neural networks, you might notice this, is that the order of these doesn't actually matter. Like if I put yesterday's temp here and then trained it like again, I would have to retrain it, but it doesn't really matter. The issue is that for pixels, the location of pixels does matter. Obviously, if you scramble all the pixels in an image, it's completely different, right? So what we do with convolutions is instead of applying this neural network to all the pixels at once, we basically take what's called a kernel and basically just apply them to part of the pixels. So I'm going to have a super small image here, just as an example. So this is like, what's 1, 2, 3, 4, 5 pixels by 4 pixels. Or let's say 5 pixels. So this is a 5 by 5 image, right? So each of these is going to be a pixel. And in real life images, let's pretend for the sake of simplicity that these are just pixel values, or just one number. So it's like a gray image. Each one of these is a number. Let's say like 7. Well, let's say it's between 0 and 1. So this is 1, 0.5, 0, 0.1. Instead of applying the neural network to all these at once, we basically group them together. And we take what's called a filter or a kernel, and we pass it over a group of pixels at a time. And then we do the same exact thing, where we multiply each of these and then add them together. So that image kind of shows a really complicated version of that. But basically, let's say here I had my kernel. Again, these are all weights, right? Which let's say my weight was 2, 4, 0, -1. So it would basically apply this to these 4. So 2 times 1 plus 4 times 0.5 plus 0 times 0.1 plus -1 times 0. So this actually just be 2, 2 plus 2, which means the output of this, right, at this section would be 4. I'm going to put that in the box. And then you simply go to the next set of pixels. So let's say this was 0 and this was 1. And you select these 4 and you apply this to it. So now it's 2 times 0.5 is 1, 4 times 0 is 0, minus 1, 0 times 0 is 0. So this is 1 minus 1 is actually 0, right? When you multiply all these, you get 0. And then you put that output here. And then you pass it over to here. And I'm not going to do the calculation, but let's say the output was 7. And what you'll notice is I do it again, I get 8. And then what I do is I go down, so I put these 4. And I get another number. And you'll notice it actually creates another image. But this time, the image has kind of been what's called convoluted, which means that nearby pixels have kind of been combined with using these weights. So that's basically just what you would do if you were using images as your data set instead of just numbers. Because that allows you to kind of combine nearby pixels. Usually also you'll notice this is one kernel here, one filter. So this would literally only be 4 weights, right? Normally you'd actually pass over like several filters. So you'd pass over like 16 filters. And that way you would have, 16 times 4 different weights. And that allows you to have more complicated neural network. Usually, also, to make the image smaller, there's also another operation you can do, which is the same thing where you pass over a filter like this, but instead it's called a max pool filter. And instead of kind of combining the pixels, all it does is it just takes the highest pixel. Super simple. So out of these, it was 0.5, 0, 0, 1, 0. So the highest value here is 0.5. So this would just put 0.5 there. And there's more information you can read online about this, or feel free to just message me if you have questions. But yeah, I'm sorry I couldn't get to the like super in detail, but essentially the convolution will multiply and add together pixels as it goes across to kind of combine nearby ones. Max pool will kind of make the image smaller by just taking the maximum image that's nearby, taking the maximum pixel that's nearby. And as you do that successively, as you can see in this image, you'll do that convolution multiple times. So the image will get smaller and smaller and smaller as you can see the image. And then at the end, usually they'll pass it through a small neural network. You can see there, they just have 2 layers of neural network. And this was an actual neural network that was one of the classic neural networks that was able to classify numbers, like handwritten numbers. And you might wonder, okay, that seems really complicated to implement in code. It really isn't that complicated because I told you previously, you said layer 1. Previously, I said, okay, you can say layer 1 equals n dot linear, right? To make your linear neural network. Well, to make a convolution, you just say n dot con 2D. Because you're doing a convolution and you're doing it usually for 2 dimensions for an image. And that's even if you have an image with RGB. If you imagine an image with RGB, you can just imagine that there's 3 images and it does all 3 at once, basically. Okay, that's it for the catch-up meeting because it's already 2:37. I don't know if you guys have any questions. Okay. Let's see if I can